Hello, today I Naveen going to prepare an audio lecture for visually impaired student from book Pradeep's Organic Chemistry Volume 3, Chapter 5, Bioinorganic Chemistry. Inorganic chemistry deals primarily with the salts and complexes metal ion, whereas bioinorganic chemistry deals majorly with the inorganic chemistry when applied to a biological system. Thus, a bioinorganic chemistry can be regarded as a branch of science that related to inorganic chemistry with the life processes by recognizing the role of metal ions in the normal growth and functioning of biological processes. In brief, bioinorganic chemistry highlights role of metal ion in biology. Bioinorganic chemistry. It is a rapidly developing area of chemistry because of its importance in the biological system. The essential biological role of a few elements have been known for many years. This chapter will focus on the important role of metals, nonmetals, and their compounds in biological processes. Section 5.1 Essential and Trace Elements. We think that the chemistry of life is solely composed on inorganic molecules. It is a wrap concept. In fact, there is a long list of inorganic compounds that are essential to living systems. For example, skeletal affect the incremental materials. Outer covering in higher animals is composed majorly of inorganic material, and the lifetime consumption of oxygen by a living entity is a major fractional of its material needs. In addition, water, oxygen, calcium phosphate, and calcium carbonate are the major inorganic constituent of living matter in terms of quantity. Table 5.1 List of the abundance of element in a earth crust and oceans compared with the some abundance in typical mammals. Abundance of element earth crust and in the ocean compared with this abundance with the typical mammals. First, hydrogen. Earth crust में है 1400 ppm. Ocean 10 की power 5 ppm. Typical mammals 10 की power 5 ppm. Second, helium 0.01 in earth crust, 10 की power minus 6 in ocean. Third, lithium in earth crust it is 20 ppm, 0.2 ppm in ocean, and 0.03 ppm in typical mammals. Beryllium 2 in earth crust, 10 की power minus 7 ppm in ocean. Next is boron 7 ppm in earth crust, 5.0 ppm in ocean, and 0.2 ppm in typical mammals. Carbon 200 ppm in earth crust, 28 ppm in ocean, and 10 raised to the power 5 ppm in typical mammals. The absence of an entry negative sign that is reliable data are not available. Data are as 10 की power n Rn of order magnitude are estimated be. Here it is an also a table of abundance of element in earth crust, ocean compared with the abundance with the typical mammals. Of all known these elements, it is about 30 elements of have been recognized as essential and indispensably of a life. On the 30 elements, 15 of them are metals, and essential elements are needed for the growth of normal function of an animal and a plant. Absence of these elements result in a surge of many malfunctionings of living organisms. Thus, an element may be considered essential when its insufficient intake process and important of normal function, and its restoring reliefs is impaired to the functions. Some of these elements are required in bulk or macroscopic amount of all the forms of life and are classified as a bulk element. Some of the bulk elements are required for a structural purpose like skin, bone, eggshell, various organs. while rest of are used as a minerals. In the other words, the absence of essential elements, the organisms can neither grow nor completely its full life cycle. The essential elements can be further divided into two subgroups. First, bulk elements. Bulk elements, essential elements, are formed in a higher concentration. Second, trace elements. Essential elements are present in a low concentration. Bulk quantity group 1 and group 2 metals are required mainly to balance the electrical charges associated with the negative charges macromolecules in the cell and also maintain the osmotic pressure inside the cell. The reaction flask of a given organism in a cell, in addition of transition elements and heavier member of P group, also plays a very important role in a bioinorganic chemistry. Some of the inorganic elements are required in a small quantity and are classified to the trace or ultra trace element. These different type of essential elements present in a living organisms are classified as in table number 5.2. Bulk structure elements: hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur. Minerals elements: sodium, potassium, magnesium, calcium, chlorine. Trace elements: iron, copper, zinc, vanadium, nickel, cadmium, lithium, lead, tin. Ultra trace elements: metal, magnesium, molybdenum, chromium, silicon, arsenic, selenium. Ultra trace elements: non-metal, fluorine, iodine, boron. It is important to note that all these elements displayed in the table number 5.2 are required by all the plants and animals. For example, sodium ion Na positive is of a special importance of higher animals. It is however not essential to many bacteria and plants except blue-green algae. The ultra-trace elements via boron, aluminium, vanadium are needed to some higher plants. Molybdenum is essential to only those organisms which derive a nitrogen from an inorganic source. Selenium is an essential micronutrient of a mammalian species but proves toxic at a higher levels. Selenium deficiency in humans results in a degenerative condition of heart tissue known as Kesan disease, named after a country in China, in which it is was endemic because of extremely low selenium level in a soil coupled with the pollution that entirely dependent on the locality of a grown grains. It is important to note that when some essential elements may prove to be toxic, it is consumed in a higher quantities. Section 5.2: Essential bulk elements: sodium and potassium. We have learned that both sodium and potassium are essential for life processes. For example, we need at least a 1 gram of sodium per day in our diet. However, because of our habit to addition salt on food, some people consume as many as 5 times more than the required. However, intake of potassium is not a problem. Instead of potassium deficiency is more common. We must include potassium rich foods such as banana, coffee in our diet. In organic chemistry, we always think of similarities between sodium and potassium. However, in biology, it is a difference between sodium and potassium which plays a very important role. Cells pumps out sodium ions of cytoplasm where cells pumps of potassium are inside. Table number 5.3. The this ion transport is called a sodium pump, and it involves both the active explosion on Na positive ion and the active take up of K positive. It is a difference in the total alkali metal of total metal ion concentration inside and outside the cell. that is produce an electrical potential across a cell membrane, which is important for a functioning of a nervous and muscle cell. Table 5.3, concentration of ions in moles per liter. Red blood cells, sodium 11 and potassium ion 92. Blood plasma, sodium ion 160 and potassium ion is 10. The transportation of ions requires energy, and this is obtained by the hydrolysis of ATP, adenosine thiophosphate. It is essential that hydrolysis of one ATP molecule to ADP, adenosine diphosphate, provides enough energy to move the 3Na positive out of cell and 2K positive and 1H positive ions back into the cell. Next, calcium and magnesium. Both calcium and magnesium are present in our fluid. Magnesium ion are concentrated in an animal cell and calcium ions are concentrated outside the cell. This is similar to the presence of K positive inside the cell and whereas sodium ion outside the cell. Calcium ions are present in external skeleton of creature such as shellfish, corals, the mineral used in calcium carbonate. Creatures with interior skeleton such as mammals and reptiles use calcium hydroxide phosphate, capetite, Ca5OH whole thrice, and the enamel of a tooth be fluoroaptic. 3 calcium 3PO4 whole twice CaF2. Both these compounds are highly insoluble. Important mineral used in biological materials are listed in table number 5.4. Calcium ions are important in blood clotting and requires to trigger the contraction of muscles such as those of the control of a beating of heart. In fact, some type of muscles cramps can be prevented by increasing the intake of a calcium ion. Table 5.4, calcium containing mineral in a biological materials. Minerals: calcite. Formula is CaCO3. Organism: birds. Location: Excel. Mineral, second mineral, argonite. Formula is CaCO3 again. Organism: Moccus. Location: shell. Third is hydroxyapatite, Ca5PO4 whole thrice OH. Organism: vertebrates and mammals. Location: bone. A decrease in calcium ion content of blood, either due to a dietary deficiency from its sufficiency of the parathyroid hormone, maybe leads to a disease styled tetany. On the other hand, an increase in the contraction of calcium ion in a blood may lead to a calcification of several integral organisms. The absorption of dietary calcium ion or a magnesium ion from an interstitial trace may be prevented as by the simultaneous ignition of a organic acid, example oxalic acid, with which it combines to form an insoluble salt. It means that the availability of direct calcium positive ion is greatly affected by the other constituent of our diet. Both calcium ion and magnesium ions are exerted mainly via large intestine instead of a kidney. Magnesium, because of high charge radius ratio and consequent strong hydration in magnesium H2O whole 6 plus 2 complex, plays a very important role and are different from those of calcium. In fact, as a counter ion to the negative charge group in a nucleotide and polynucleotide. One of the most important nucleotide is ATP, adenosine triphosphate, which serves as fundamental energy source for a living cell. ATP is thus known as an energy-reaching molecule and used to derive the most of these chemical reactions of this cell. Magnesium ion from a complex with ATP, it has been observed that all the trans phospho transphosphopoly polari- transphosphorylation reactions involves ATP processed smoothly in the presence of magnesium ion. ATP is an adra- anhydride of phosphoric acid. The hydrolysis of anhydride is a very favorable reaction. Thus, hydrolysis of ATP to ADP shows in the equation below in liberates 30.7 kilojoule per mole and 7.3 kilocalorie per mole of energy at pH 7. The living systems thus utilize this energy requires biochemical processes. Here we have phosphoric anhydride ATP plus 2H2O. Hydrolysis, it gives ADP plus inorganic phosphate and plus H3O positive ion. It has been observed experimentally that the activating effect of magnesium ion transphosphorylation may be duplicated in virat by Mn2, calcium 2, CO2, Zn2 and nickel 2 positive. The most of these aspects of biochemistry of magnesium it plays a very important role in photosynthesis. Magnesium containing chlorophyll using energy from the sun converts carbon dioxide and water into sugar and oxygen. Here is the reaction 6 molecules of CO2 gas plus 6 molecules of H2O liquid. It gives C6H12O6 aqueous plus 6 molecules of O2 gas. Without the oxygen from a chlorophyllic reaction, these planets would still be surrounded by a dense layer of carbon dioxide. In addition, without of a sugar energy sources, it would have been difficult for our life to progress from a plant to animal. It is very important role of magnesium ions sits in the middle of the chlorophyll molecule and holds the molecule in a specific configuration. Magnesium has only a one possible oxidation number, that is plus 2, and as a result the electrons transfer reactions involves photosynthesis can proceed without interference from the metal ion. Third is phosphate. Phosphorus is a very important element for our life processes. For example, free hydrophosphate PO4 whole thrice PO4 3 negative and dihydrogen phosphate H2PO4 negative are involved in a blood buffering system. Phosphate is a linking unit in the sugar ester of DNA, deoxyribonucleic acid and RNA, that is ribonucleic acid. The phosphate unit make up a part of ATP, essentially energy stored unit in a living organism. Bone is a phosphate mineral, a commonly called mineral apatite in a calcium hydroxide phosphate Ca5OH whole thrice. The presence of sodium in bone and its function is regular of pH of calcium constituent important features of phosphate. It is important to mention that the normal formation of bone depends on the relative amount of direct phosphorus and calcium in addition of vitamin D. Section 5.3 Essential Trace Elements. Among all these non-trace elements, the three most prominent biological active metals are iron, copper, and zinc. The remaining trace elements, excepting boron, fluorine, are used in a very small amount, less than 10 mg in adult human, and are referred as ultra trace elements. The trace elements are known to play a very important role in metalloenzymes. Iron is an essential in a small amount of both plants and animals in a life. However, like copper and selenium is a toxic when used in a large quantity. Biologically, iron is a very important transaction element, and it is found at greatest abundance in a biological system in the form of porphyrin complex heme as such as hemoglobin and myoglobin. Porphyrins are microcyclic ligands with the derivative of porphyrin discussed later. A human body weighted of 70 kg contains about 4.3 gram of iron. Nearly 70% of this iron is present in hemoglobin and 3% in myoglobin. Remaining 23% of iron is present in ferritin. The ferritin is present in the spleen, liver and bone marrow. It consists of a shell of linking ammonia amino acids, that is peptides, called aproferritin, surrounded a core of an iron 3 oxohydroxophosphate. The core is a cluster of iron 3 ions, oxide ions, hydroxide ions, phosphate ions with the composition FeOOH8, FeOPO3H2. It is a very large and containing 45,000 iron ions, which its hydraulic coating with this large aggregate it with water molecule and concentrated in a spleen, liver and bone marrow. Apoferritin protein can be prepared from a ferritin by reducing ferric iron to the ferrous at a pH 4.5, followed by removal of Fe plus 2 by dialysis. The formula weight of apoferritin is nearly of 46,500. Ferritin can also be synthesized in a laboratory with the process of similar to the natural ferritin. It can be prepared by treating crystalline apoferritin with an inorganic iron 2 salt in presence of oxygen. Ferritin is probably formed in vivo of an analogous process. The various steps involves the pathway of Fe2 positive from blood stuffs to hemoglobin and to ferritin involves in the processes. First is the Fe plus 2 on the blood directory material is reducing to Fe plus 2 in a interstitial tract. After the absorption into the cell of interstitial mucosa, Fe plus 2 is incorporated with the ferritin as Fe plus 3. The Fe plus 2 in a mucosa is also converted to Fe plus 3 plasma bounded by iron binding globin named as transferritin. Plasma Fe plus 3 is in equilibrium with the iron in liver, spleen and bone marrow. The flow changes are these occurs summarized in a scheme 5.1. The scheme 5.1 pathway of iron 3 from a stuffed food to the hemoglobin and to the ferritin. फर्स्ट क्या है हमारे पास Fe plus 2 it changes into Fe plus 2 in heme, Fe plus 3 in bounded interconvertible in serums and transferritin in porphyrin. Fe plus 2 to Fe plus 3 ferritin in liver, cell and bone marrow. Next is zinc. Among all these trans elements, zinc is secondly only to the important only to iron is important. Zinc is an essential to all these living organisms and plays an important biological role in enzyme systems of animals and plants. Human contains about 2 grams of zinc and is one of these important crucial element in our diet. Deficiency of zinc are not life threatening but contribute to the fatigue, lethargy and related symptoms. Zinc plus 2 ion is a soft acceptor compared to other divalent ions like magnesium plus 2, calcium plus 2, manganese plus 2 and acts as a stronger Lewis acid towards many biological molecules. Compared to zinc plus 2 ions, copper plus 2 ions is also soft but as an redox reaction and complicated its behavior. The complex of zinc ion are much more liable than the corresponding complex magnesium plus 2, nickel plus 2 and manganese plus 2. This facility of the role of zinc ions in enzymes. Since Zn plus 2 ion is completely resist to redox changes at biological potentials, it is a role can't be affected by the changings the redox potentials in the organisms. A number of enzymes containing zinc are known. The most important of all these enzymes is the carbonic anhydrase. It is present in red blood cells and it involves in respiration. It speeds up the absorption of carbon dioxide by red blood cells in muscles and other tissue. By on the other hand, in the reverse reaction, it involves releasing of CO2 in the lungs. The reaction of pH is dependent. CO2 aqueous plus H2O. In presence of carbonic, it gives H2CO3 aqueous. It is irreversible and gives anhydrase. Thus, the zinc-containing enzyme carbonic anhydrase catalyzes the otherwise slow carbonic acid carbon dioxide equilibrium reaction. The carbonic anhydrase has a common four coordinated environment around zinc ion with thus which three of the ligands are imidazole nitrogen of the three histidine and the fourth is the water molecule of the hydroxide ion as well in given below. A water molecule is coordinated to a zinc has a pK near 7 and the role of zinc is reduced to a basicity of hydroxide ions such as high effective concentration of hydroxide can exist be approximately neutral medium. Another important enzyme containing zinc plus 2 is an carboxypeptidase. It is present in pancreatic juice and is primarily involved in the digestion of protein by animals and protein metabolism in plants and animals. This enzyme catalyzes the hydrolysis of terminal peptide amide link of carboxyl end of peptide chain. The enzyme is selective and works only with the R group in the internal terminal amino acid in aromatic or a balanced aliphatic chain such as an L configuration. Here carboxypeptidase during hydrolysis it gives the following product. The next is copper. Copper is the third most biological important transaction metal after iron 4.1 gram and zinc 2 gram. The human beings needed around 8 milligram of copper daily. A deficiency of copper thus optimize a value of result in the inability of animal to use iron stored in a liver. As a result, the animal suffers from anemia. The copper in a bound of proteins in our body either of metalloprotein as an enzyme. Excess of copper is highly for food good look. Human beings can excrete an excess of copper, but a biological defense can result in a copper accumulation in the liver, kidney, and the brain. The illness caused by copper is called Wilson disease. It is an hereditary storage of ceruloplasmic causing copper accumulation in the liver, kidney, and the brain. Patients suffer from Wilson disease are cured by administering ethyl diamine tetraacetic acid that is EDTA which forms a soluble copper complexes. The soluble copper complex can be excreted harmlessly through the urine. At the same time, many other essential metals involved in enzymatic reactions from EDTA complex are excreted. Thus, EDTA treatment can be aspects many unwanted enzymes reactions. As a result, utmost care should be taken in monitoring Wilson diseases. Imocyanin is a copper-containing protein which is important as an oxygen carrier in some invertebrate animals. Despite its name, it is a non-heme protein. It is found that in blood of snails, carps, and lobsters, octopus, and scorpions. The oxygenated hemocyanin are of blue colored. Unlike human blood, has one dioxygen molecule attract to the two copper atoms. Deoxygenated hemocyanin contains copper 1 and it is of blue. Next element is selenium. Selenium is essential to health. All case of organisms metabolize selenium. In humans and other mammals, serious disease arise from the either excessive or insufficient hereditary seleniums. The toxic effect of selenium have been long known, particularly for grazing animals. In soil with high selenium content, some plants accumulate large amount of selenium as methylcyanine in order to keep selenium away from the metabolic machinery. Animals that graze that selenium accumulation plants develop toxic reactions in a blind stage and alkali diseases. Selenium poisoning in humans is rare, but has occurred. Very mines have caused selenium to be released from the soil into drinking water supply. Loss of hair and nails is seen in case of human selenium toxicity and followed by anemia and jaundice. Although selenium is a toxic at high levels, selenium is an essential micronutrient for mammalian species. A selenium deficiency in human results in a degradative condition of heart tissue known as Keisan diseases. The disease named as after a country in China. The accepted minimum daily requirements of selenium for adult human is 70 micrograms. Many of type of food provide selenium, particularly seafood, meat, grain, and onion family. The mammal and the birds requires a selenium for production of an enzyme glurothatonine peroxidase, hydrogen peroxidase and organic peroxidase, which cause oxidative damage to cellular component and enzymatically destroyed by the selenoprotein. Such antioxidant activities such as the glutathione peroxidase and therefore selenium protects against oxidation induced cancer. Next element is chromium and molybdenum. Trace amount of chromium and molybdenum are necessary in our diet of mammals. Chromium 3 and insulin are both involved in maintenance of a correct level of glucose in our body. A deficiency of chromium 3 of an inability to use the chromium 3 ion results in removal of glucose from blood as fast as normal as to leads to diabetes. Compound containing chromium, for example dichromate and chromate, when indigested or absorbed through a skin are carcinogen. Therefore, utmost a case of must be taken while K2CR2O7 or K2CR04, especially while performing titration. Molybdenum is a most biological important member of an chromium family. It is the heaviest atomic number element to have a widely range of function in living organism. The most important molybdenum enzyme which contains iron as well is nitrogenase. Thus, nitrogenase contains two protein, molybdenum ferredoxine and azoferredoxine. Molybdenum ferredoxine is an air-sensitive and brown-colored species containing two molybdenum atom, 24-36 iron atom, 24 to 36 sulfur atoms together in a protein. It has a molecular weight about 2,25,000. Exoferidioxin is yellow, air sensitive, and it is derivative of foridoxin, Fe4S4SR whole 4. It has a molecular weight of range 50,000 to the 70,000. The enzyme nitrogenase occurs in a bacteria and reduces that inert dinitrogen of atmosphere to ammonia iron. This reaction is used in a synthesis of protein by plants. Let us have an idea of importance of this enzyme by typical example. The amount of dinitrogen fixed biological is estimated to be 175 million tons per year compared with the total of 110 million tons of NH3 produced by the Haber-Bosch process in distillation of a coal. Question is given. Question 1 is, why is the metals are of rare of molybdenum so biological importance? Answer. There are several reasons to be addressed in this question. First is, the molybdenate ion MoO4 negative has high aqueous solubility at a near neutral pH value, making it easily transportable by biological fluids. Second, the iron has a negative charge, making it more suitable for a different environment that can have a cation for a period for transition metals. Third, the element has a wide range of oxidation state +4, +7, +4, +5 and +6 whose redox potential overlaps with those of biological systems. Fourth, being a soft Lewis acid, molybdenum 4 shows a strong bonding preference for the soft Lewis base sulfide, another important component of our enzyme. Next element is nickel. The biochemistry of nickel is poorly understood of all these periods for transition element, and it is present in some enzymes systems in the form of porphyrin type complexes. Some of the tropical trees concentrated nickel to such an extent with that makeup of 15% of their dye masses. It is a highly toxic to the most plants and moderately toxic to mammals. Next element is cadmium. Cadmium is a toxic element and it is present in our foodstuffs and normally indigested at a level R of close to maximum safe level. Kidney is the organ most susceptible to the cadmium. Cadmium indigested 200 ppm case serves damages. Cigarette smokers absorb significant level of cadmium from tobacco smoke. Exposure to cadmium from an industrial sources is a major concern. Use of nickel cadmium battery is a cadmium battery so that the cadmium metal can be safely recycled. Next metal is mercury. Mercury is a hazardous because it's relatively high vapor pressure. The mercury vapor is absorbed in the lungs, dissolved in the blood, and thus carried to the brain. This causes irreversible damage of central nervous system, and it is slightly soluble in water because of their weak metallic bonding. Inorganic compounds of mercury are less toxic and theirs have less solubility in the water. Next element is arsenic. Arsenic is an element essential to life. However, we need to ultra trace amount of this element. Anything more than the tiny amount of cause of arsenic poison. Arsenic in a measurable quantity cause death through the enzyme inhibition. Next is non-metals. Non-metals among the essential elements are hydrogen, carbon, oxygen, nitrogen, phosphorus, sulfur, chlorine and iodine. Majorities of these needed in a trace amount except carbon, hydrogen, nitrogen, oxygen are abundantly available in a constituent most of these chemicals in the living system. First non-metal is phosphorus. Phosphorus is an essential element in our life for our life. Its constituent an important plate of energy-rich molecule known as ATP, adenosine triphosphate, and it is also an important component of a bone as a apatite, Ca5 PO4 whole thrice OH, calcium hydroxide phosphate, partially formation of fluoroapatite, that is CF5PO4 whole thrice F, strengthens the structure of teeth and make it soluble less soluble in the acid forms and fermenting organic material in the teeth. Next non-metal is iodine. Nearly 75% of iodine present in our human body is located at one place, that is thyroid gland. It is used in synthesis of hormones thyroxine and thyroid thionine. The hormones are essential for growth and the regulation of neuromuscular functioning and for of the maintenance of male and female reproductive function. One common cause of goiter is lack of iodine in our diet. A symptom of goiter is swelling over a part of neck. The enlargement of this attempts to the thyroid gland to maximize absorption of iodine in iodine deficiency circumstances. In order to remove iodine deficiency, potassium iodide is added to the common household salts, such as salt is iodized salt. Third non-metal is chlorine, Cl negative ion. The chlorine ion has a vital role in a ion balance in our body. It doesn't appear to be play an active role, but it is simply acts as a balance of positive ions, that is sodium and potassium. It is a major anionic found inside and outside the cell. It is then essential as NaCl electrolyte for higher mammals and plants. Chlorine ion is essential in digestive juices. Deficiency of chlorine ion is in fact leads to impaired growth. Nearly 30 elements are recognized as essential elements for at least some forms of life. It includes most of the three elements through the atomic number 35 except beryllium, aluminium, scandium, titanium, gallium, germanium along with the noble gases. Molybdenum and iodine are the also essentials. It is interesting to note that all the elements appreciably abundant in our human body, with the exception of phosphorus, are abundant in a sea water, suggesting without the doubt of our families in our roots in the sea. Chemicals abundance in elements in human body are hydrogen 63%, oxygen 25.5%, carbon 9.5%, nitrogen 1.4%, calcium 0.31%, phosphorus 0.22%, chlorine 0.03%, potassium 0.06%, sulfur 0.05%, sodium 0.03%, and magnesium 0.01%. Section 5.4 Metalloporphyrins. Porphyrins constitute an important class of bioinorganic compound. It is a metal ions of surrounded by 4 nitrogen of a porphyrine ring. Porphyrins are macrocyclic tetradentate ligand made up of 4 pyrrole links linked together for the methane bridge as shown in figure. This tetradentate ligand has conjugated double bonds in the system for nitrogen donor site. 2 of the nitrogens are tertiary nitrogens while remaining of 2 are the secondary nitrogens. Thus, tertiary nitrogen's atoms forms a coordinate bond by donating its lone pair to the metal, and the coordinate bond is such as allowed the arrowhead from from ligand nitrogen to the metal ion. The other two secondary nitrogens have lost a proton. Each of these have forms a covalent bond with the metal as in. Thus, the porphyrine ring serves a tetradentate di-negative ligand. As a result, di-positive cation like iron, magnesium, nickel will form neutral complex with porphyrine, which is a process loses to a proton such as in given figure. When 4 pyrrole rings of porphyrine are substituted by organic group, other than the hydrogen, it is called a porphine. Thus, porphines are microcyclic tetrapyrrole system which has conjugated single double bond together with the various group other than the hydrogen substituted at the periphery of the ring. The substituent attached to the rings are usually organic group and electron withdrawing on the releasing or electron releasing characteristics. The complex formed by the porphines with the metal generally di-positive called metalloporphines. These are biological importance compounds and plays a very important role in a animal to a plant's kingdom. Porphine ring systems are fairly rigid body of delocalizing of an electron in a molecule. Although the skeletal system is fairly rigid, significant variations have been observed among the metalloporphines in the interatomic distance between a pyrrole nitrogen and the metal at the center determined the size of central hole. From a knowledge of covalent bond radii, one can estimate that the bond between the three nitrogen atom and the atom of a first transition series should be 2 angstrom long. In brief, an ideal size of an atom to fit in a hole of 2.0 angstrom. Thus, the size of hole in this center of porphine ring is ideal for a accommodation of metal ion of first transition series of higher alkali earth metals. A metal iron is appropriately sized sitting in the center of porphine ring will be surrounded by 4 nitrogens of pyrroles and forming a square planar geometry. It means that the metal ion has a 4 nitrogens lie in the same plane. However, when the size of metal ion is smaller than the ideal, the ring will be reclocated to accommodate the precise the metal ion. In this way, the ring will either readjust or distort itself in the order to accumulate the metal ion. On the other hand, if the size of metal ion is larger than the ideal size, the transition metal is can't fit it in a hole and say out of the plane for nitrogen. It means that it means that the metal atom sits above the plane of 4 nitrogens and acquires a square pyramidal geometry. The nature of metalloporphines varies with the nature of metal ion and the type of inorganic compound attached at a eight positions of a 4 pyrroles around the periphery of a porphine. A group of related compound with halocyanin are electricals within porphines. These compounds are intersecting because of their intensive colored metal complex which are of almost at most a commercial application in dyes and pigments. The size of hole is the phthalocyanin ring is about 0.1 angstrom smaller than the porphine ring of the result nitrogen atom compared with the carbon. Compare covalent radii of carbon is 0.77 angstrom and the nitrogen is 0.75 angstrom. Molecular structure of a metal phthalocyanin complex. The two of the most important metals complexes of porphines are chlorophyll and heme, which are being discussed. Chlorophyll 2 is a magnesium complex of porphine which plays a very important role in photosynthesis. Photosynthesis is a remarkable redox reaction in which a conversion of water and carbon dioxide into a sugar and nitrogen in presence of sunlight. This process is the primary source of the food and we ate the molecular oxygen when we breathe. The function of chlorophyll molecule is to absorb photo in a red part of the visual spectrum 700 nanometer and pass this energy to the excitation of other species in the reaction chain. The ability of absorbed to the light is due to the conjugated polyene structure of the porphine ring system. The role of the magnesium is to make the entry molecule rigid so that the energy absorbed is not easily lost. There are a number of similar but not identical chlorophyll molecules. It is a very important note that chlorophyll to a basic porphyrin system has to be modified in two ways. In pyrrole ring 4, one of the double bond has to be hydrogenated to form a magnesium dihydride porphyrin complex. In addition of cyclopentone rings has to be fused to the other pyrrole ring 3 as shown. This is a chlorophyll A. In brief, the absorption of sunlight by chlorophyll is a first step in conversion of sunlight into unstable energy by plants. It will not be out of the place to say that chlorophyll is as a nature solar energy collector. Heme is an iron 2 4 which is present in hemoglobin and myoglobin, which is being discussed given below. Section 5.5 Hemoglobin and myoglobin. The molecular oxygen plays a very important role in a biological system because of an importance in respiratories of the formulations of oxygen. We have already learned that the nature involves a number of reactions such as a redox reaction, electron transfer and atom transfer and photochemical reaction. A number of proteins are known as a bind and transfer to the different extent, such as a protein binds called oxygen carriers. The most of these important well-known document for protein that binds the transfer of oxygen are hemoglobin and myoglobin. Hemoglobin and myoglobin are very closely related to each other. Hemoglobin is a very large protein with a molecular mass 64,500 and contains 4 subunits. Each subunit is made up of a heme group associated with the protein called globin. It is important to recall that each heme group is composed of a Fe plus 2 ion surrounded by the 4 nitrogenous of porphyrin ligands. Hemoglobin is a larger intermolecular protein that is responsible for red color of blood cells. On the other hand, myoglobin is a relatively small protein with a molecular mass 17,000 and consists of a one heme group and a polypeptide chain. It is important to recall that the peptide chain consists of 150 to 160 amino acid reduced to folded about the single heme group. Myoglobin MB is a small intermolecular protein in vertebrate molecules. Myoglobin was the first protein whose X-ray structure was established in 1959. In 1962, Nobel Prize in Chemistry was awarded to Candever and Petrit for their work on structure of globular protein inside myoglobins. The basic function of hemoglobin and myoglobins are given below. Hemoglobin picks up oxygen in lungs and transports in our rest of the body. Myoglobin accepts the oxygen, forms the hemoglobin in muscles and store it until needed for energetic processes. Third, deoxygenated hemoglobin use some of these its amino acids to fix up CO2 and transportation of CO2 back to the lungs. Oxygen carrier performs the function of acquiring O2 from atmosphere, transporting it to the circulatory system of the organisms and deliver it to the location where it is used. They all binds O2 rapidly and reversible according to the equation 1. Protein plus O2 equilibrium with the protein O2. The equilibrium must be largely to the right at the oxygen concentration available to pick up location. From the example, lungs, air interface, muscle blood cells interface, and mother fetus interface at the placenta. It is an important role. It is important to note that the oxygen carrier interact strongly with the oxygen to bind it. However, the carriers must not undergo irreversible oxidation in the process. In a brief, hemoglobin picks up the oxygen in the blood and transport to its sites of use inside the muscle cells. This oxygen is transferred to the hemoglobin, which stores in alternate until required from metabolic action in a O2, which is O2 is reduced to CO2. Deoxygenated hemoglobin then transports CO2 back to the lungs. Structure of hemoglobin and myoglobin. We have already mentioned that the structure of hemoglobin and myoglobin are very close related to each other. Hemoglobin is a largely protein consists of four subunits and each subunit contains heme associated protein globin such as in figure number 5.4. Occurrence in the protein complexes of hemoglobin and second point 54 point A is hemoheme and 54 of B is systematic wave of oxygenated heme in a hemoglobin. The iron is held in a positive by the coordination with the nitrogenous of heme and the imidazole of globin complex. This complex reversibly with the oxygen as shown in a figure 5.4b. Thus, a hemoglobin in the oxygen carried by the blood and the red color of a blood is due to oxygenated hemoglobin. It is important to note that the four site units are similar but are not identical. Two subunits from alpha chain of 144 amino acids while other two subunits from beta chain are of 146 amino acids. These chains are called together to give a three-dimensional network systemic structure of hemoglobin shown in a relationship of four subunits of tetrameric if shown in figure 5.5. Structure of myoglobin. Myoglobin is a small protein compared to hemoglobin. It consists of a single heme group embedded in a polypeptide chain called globin. The peptide chain consists of 150 to 160 amino acids folded about a single heme group as shown in figure 5.6. The heterocyclic ring system of heme consists of porphyrin containing pyrrole group labeled as A, B, C, D, linked by methane branches. The iron atom in the oxidation state to Fe plus 2 is present at a center of heme is bounded to the nitrogen of a porphyrin system together one nitrogen atom of a imidazole side chain of histidine reduces which is a part of a long protein chain of amino acid reduces. It is a polypeptide chain that has plays a very important role in biological fixation of molecular dioxygen. A simple outline of the structure of myoglobin shown heme embedded in a polypeptide chain as shown in the figure 5.6. It is important to note that both the hemoglobin and myoglobins have a coordinated iron atom. The oxidative state of iron in hemoglobin and myoglobin is plus 2. Iron atom is bounded to the 4 nitrogen atom of a pyrrole ring porphyrin and fifth nitrogen is from a protein chain. If the both of these compounds the sixth position is occupied by weakly bonded to water molecule. Hemoglobin and myoglobin in such molecules are namely as deoxyhemoglobin and deoxymyoglobin respectively. However, when one molecule occupies sixth position and which is trans to histidine chain, then the molecules name as oxyhemoglobin and oxymyoglobin. The myoglobin polypeptide is comprised sorry comprised to 8 separate right-handed alpha helix designated from A to H are connected by the short and non-helix region. Role of hemoglobin and myoglobin. Hemoglobin and myoglobin plays a crucial role in the transportation of oxygen from lungs to tissue and the CO2 that is HCO3 negative from tissue to lungs. The function of hemoglobin is to bind O2 at a high oxygen. Partial pressure of the lungs tissue from the oxygen is HbO2. Hemoglobin carries this oxygen without the loss of the blood and then released in the myoglobin. In other words, the dissociated oxygen from hemoglobin diffuses to the tissue, whereas myoglobin picks up it's the stored until it's needed. It means that the myoglobin has a great oxygen affinity that a myoglobin to a partial pressure. The hemoglobin and the carbon dioxide CO2 and are returned to the lungs, whereas CO2 is exhaled. The sequence of separate can be represented as shown given below. CO2 is O2 is inhaled by the hemoglobin, binds with hemoglobin and reaches to our cell. Respiration is occurs and this hemoglobin oxygenated blood is goes to the tissue and there is a reaction between reactions occurs, that is it is clear from this scheme that both hemoglobin and myoglobin plays a cyclic in the transportation of O2 from a lungs to tissue and CO2 from a tissue to lungs. The CO2 is carried out in a form of HCO3 negative ion, that is CO2 plus H2O. It gives H positive plus HCO3 negative. Carefully analysis of this scheme suggests that the partial pressure of O2 is higher in lungs, about 100 torr, and this is responsible for formation of HbO2 hemoglobin, oxygenated hemoglobin. However, the low pressure of O2 in the tissue, that is 20 to 30 torr, is responsible for dissociation of oxygenated hemoglobin. The dissociated oxygen O2 diffuses into the tissue and dioxides as metabolic fuels of 2 CO2 and water. The carbon dioxide evolves in exhaled in the lungs. Oxidation and oxygenation of hemoglobin and myoglobin. The heme group consists of Fe plus 2 ion embedded in a porphyrin ligand. Fe plus 2 has a 6 coordinating sites. Porphyrin ligand take up of 4 of the 6 sites, leaving two free binding sites on the opposite side of the metal ion. If the free heme is present in aqueous solution, then two vacant sites may be occupied by the water molecules. In the aqueous solution containing oxygen, a free or a naked heme group binds to the oxygen molecule in an irreversible manner with the oxidation of Fe plus 2 to Fe plus 3 ion. The oxidation of ion has from Fe plus 2 to Fe plus 3 destroys the oxygen binding capacity of iron. This unproductivity oxidation of biological system is heme plus 2 in presence of O2. It gives hematide Fe plus 3. The reversible oxidation of a free heme is present to the oxygen involves a series of dimerization consists of two iron plus 3 ions and iron plus 3 ions, iron plus 3 O iron plus 3 as shown in figure 5.7. Formation of hematine contains U-oxo bridge dimer of Fe plus 3 complexes. This dimer is known as hematide. This dimer can no longer act as oxygen carrier. Deoxymyoglobin DoxyMB is a 5 coordinated high spin Fe plus 2 complex of T2G4 Eg2 with the 4 of these coordinating sites of iron being occupied by the 4 nitrogen of porphyrin ring, while the 5th coordinating site is occupied by the nitrogen of the imidazole ligand of histidine reduces to joins the heme with the protein. In the absence of O2, the ligand field is weak and such 5 coordinating heme complexes Fe plus 2 are always of high spin. The diameter of high spin T2G4 Eg2 iron 2 ion has a larger than that of the central hole of porphyrin ring. The estimation of Fe and bond distance is about 218 picometer in high spin Fe plus 2 complex, while size of the whole porphyrin ring is 200 ppm. As a result, iron is compelled to 0.40 amstone about a plane of the iron formed for 4 nitrogen atoms to give a square pyramidal arrangement. Thus, distortion of a bond around the iron is given. In this, Fe lies about 70 picometer above the plane and gives square pyramidal structure with the lying above the Fe lying above the plane of the porphyrin ring. When oxygen bonds at the 6th position of iron opposite to the histidine, the Fe plus 2 contracts and the moves into the plane of a ring. In the other words, Fe plus 2 becomes coplanar. This happens because of moment of oxygen gets coordinated to the Fe plus 2. The ligand field becomes strong and the results is spin pairing. You recall that the spin pairing always leads to the low spin complexes. In this case, the electronic configuration of iron is plus 2 and changes to T2G6. Thus, a result complex is diamagnetic and Fe distance is approximately B200 picometer, which is matched to the size of whole of porphyrin system as shown. Fe is a coplanar with the rings. Oxyhemoglobin has a low spin octahedral complex. It is very important to note that the binding of a molecular dioxygen to the 6th position of the role of an atom is deoxyhemoglobin or oxyhemoglobin release the strain in a 5 coordinated system. This hemoglobin strain is compensated by loss of spin paired energy in going from 5 coordinated deoxyhemoglobin to the deoxymyoglobin to 6 coordinated oxyhemoglobin and myoglobin respectively. It means that coordination of O2 will cause a Fe plus 2 to the drop of the plane of a heme group. The shrinking of the size of iron plus 2 has a dropping into the plane of porphyrin ring as shown in a figure. The dropping of Fe plus 2 into the plane of porphyrin results in the perturbation in the imidazole group of the histidine, reduces the presence of a transposition. In the other word, decrease size of Fe plus 2 ion in the sense of imidazole group of histidine reduces, which behaves like a spring, and doing a Fe plus 2 moves the histidine molecules causes a conformational changes in a globulin chain. Since the chain of hydrogen bonded to the other units, it is the conformation as well as not affected of this interaction in myoglobin and hemoglobin. In increase of its ability attracts of O2, the second heme site of and so on. It means that one iron binds an oxygen molecule, the molecule shape changes to make binding additional oxygen molecule clusters. Since each heme is a hemoglobin about of one oxygen molecule, the process of continuance yields the carrier a maximum of 4 molecules of oxygen. This phenomena is called cooperative effect of autocatalytic nature of O2 binding. Next section is 5.6 myoglobin and hemoglobin function and cooperativity. The function of hemoglobin is to bind the molecular oxygen O2 at higher oxygen partial pressure found in the lungs and tissue and carries with the loss of the blood to the tissue. With myoglobin picks up the O2 from a hemoglobin. The sequence indicates that the myoglobin has a greater O2 affinity than the hemoglobin at low pressure of oxygen. Next section is 5.7 nitrogen fixation. There is a large amount of N2 gas, that is 78% in atmosphere. However, plants are not able to utilize this N2 because of its relative unreactive nature. The unreactive nature of dinitrogen is of ascorbic. Its very high bond strength 945 kilojoule per mole due to the presence of triple bond of two nitrogen atoms. Soils that are very fertile contains nitrogen in a form of nitrates NO3 negative and nitrites NO2 negative, ammonium salts of NH4 positive of or urea NH2CONH2. All these compounds are absorbed from a soil water together to the root of plants. The continuous uptake of nitrogen by plants reduces the fertility of the soil. In order to fix the nitrogen, that is to make a nitrogen reactive apart the substance of to produce nitrogen compounds. It is a necessary to use a energy rich condition. The process of conversion of atmospheric nitrogen into useful compounds such as ammonia is called nitrogen fixation. In 1965, Kasser Senoff, a Canadian researcher student of University of Toronto, was studying the reaction of ruthenium 3 chloride with hydrazide hydrate. He synthesized a brown compound of a combined ruthenium 3 chloride with the hydrazide hydrate but was unable to explain the chemistry composition of the compound formed. One fine day, during a discussion of another chemist, he got an idea that this brown compound may be containing dinitrogen N2 bonded to the ruthenium metal, similarly to the bond of carbon dioxide with the transition metal. He reported this excited news to the supervisor Berlin Allen. After several months, Senoff and Allen submitted to a manuscript of research finding to the journal for publication. The manuscript was rejected because of dinitrogen is known as to be inert in a noble gases. However, Senoff and Ellings again appeared to the editor of journal. The editor sent the received manuscript to the 16 other was published. 16 other celebrated inorganic chemists for comment, and they are already accredited with the discovery and research for paper here was published. As a result, world inorganic chemistry was changed, suggesting that dinitrogen is no longer unreactive and the first compound of dinitrogen was born. The first dinitrogen compound of dinitrogen can be readily prepared from aqueous ruthenium 3 chloride using hydrogen hydrate in aqueous solution. The penta-amino dinitrogen ruthenium 2 cation RuNH35 and 2 was formed and could be isolated. It is a variety of salts. Today, almost all these transition elements are known to be of dinitrogen complex, and more than 200 such complexes are being well characterized. The several new methods have now born to prepare the complex containing penta-amine dinitrogen ruthenium 2 cation. A direct method involves the nitrogen gas involves the prior reduction of a penta-amine ruthenium 3 salt with the zinc amalgam as the strong nucleophilic nature of dinitrogen group is shown in the reaction, and thus the coordination water is easily displaced by the gaseous nitrogen. Another interesting example of a strong nucleophilic nature of dinitrogen is shown by formation of a bridged complex. The another general method of preparation of this metal complex of dinitrogen involves the reduction of metal complex, especially of molybdenum and tungsten, in the presence of suitable co-ligands such as N2. Here we have a complex of molybdenum in presence of N2. Catalyst is here sodium in presence of toluene. PMA2PH, it gives cis complex containing N2. The dinitrogen can coordinate it to the metal in four ways as shown here. However, and-on modes are as well as exemplified in structure 1 and 2. N2 has a heptacity E1, heptacity 2, heptacity 2, heptacity 2. The formation of stable dinitrogen complex leads to struggy, the other transition metal. Complex with titanium 2 are most promising. It has been found that the titanium 2 alkoxide can easily reduce with the subsequent release of ammonia or hydrazine. A complete cycle of the reaction despite the fixing of atmospheric dinitrogen to the ammonia is reported. An X-ray study of the RuNH3 N2 N2 plus 2 complex indicates that RuNN linkage is linear. In a related compound CO53P3N2H, here the co-ligand is 53, P is a triphenyl phosphine, and the molecular structure is this. Molecular structure of CO53P3N2H. CON and linkage is of almost of bond angle is 178 degree. The bonding in N2 complexes resembles that of carbon monoxide complex. The back bonding of electron density from a metal into the anti-bonding of orbital is clearly reflected in the shortens of CON bond. Cobalt N bond, that is 1.807 angstrom, which is closer to the CO bond, that is cobalt CO bond 1.753 angstrom. Then the CONH3 bond 1.95. In a amine complex, the NN bond length is 1.112 angstrom, is longer than the found to be in molecular nitrogen 1.098 angstrom, suggesting a weakening of nitrogen-nitrogen triple bond of the electron density in the antibonding orbitals of nitrogen. Compares the value of 1.116 angstrom for bond order of 2.5 for N2 positive. Our several hundred compounds of molecular nitrogen with the transition metals are known today. These new discoveries were stable and metals the dinitrogen complexes leads to extensive investigation of the possibilities of nitrogen fixation. In the other words, the major interesting lies in the converting metal N2 complex with the appropriate reducing agent to convert N2 into ammonia under abundant conditions. Dinitrogen transition metal complexes of MO and molybdenum and tungsten have been shown to the promoted the coordinating dinitrogen into diazine NH, isodiazine NH2, azido NH2, hydrazine NH2. For example, trans complex of metal N2 DPPE2 plus HX at 20 degrees Celsius, it gives a complex and gives nitrogen gas. Here the metal is molybdenum or tungsten. Here the X is halide and DPP is a diphenyl phosphodiene ethane. The reduced product N2H2 has been assigned and diazine structure NH double bond NH. It acts as the 2-electron donor. All the attempts of the reduce N2H2 further N2H4 or NH3 by using stronger reducing agent have not made their successes. On the other hand, dinitrogen metal complex with monodentate CO ligand have successfully been reduced to give an ammonia. For example, the complex of 6 trans metal nitrogen 2 PME2 PH4 associated with the monodentate CO ligand dimethyl phenyl phosphine on treatment with H2SO4 in presence of NaOH followed by distillation affordable high yield of ammonia with the trace of hydrogens. Here is a reaction. In case of tungsten complex, the yield of ammonia evolves has been found quantitatively, whereas only 66% of ammonia is evolved in case of corresponding molybdenum complex. In case of H2SO4 is replaced by hydrogen halide, the intermediate is isodiazine complex is formed, which upon subsequent reaction with H2SO4 in methyl alcohol followed by the distillation affording ammonia as a shown. A similar reaction of trans tungsten N2 whole twice PME PH2 whole 4 with the HCl in a methanol liberates ammonia directly without the formation of any isodiazine complex. It is interesting to note that in case of that solvent, this solvent is changed from methyl alcohol to CH2Cl2 hydrogen and the hydrogen is formed. The chemistry of molybdenum and tungsten has been extensively studied. A reasonable mechanism is this given below. A careful inspection of the reaction sites above the reveals that the fixation of N2 to NH3 in the stable N2 complexes metal involves that the replacement of CO ligands such as tertiary phosphine which stabilize the lower oxidation state with ammonia ligands such as halide or a sulfate which stabilize the higher oxidation state. The process promotes the electron transfer from metal to nitrogen or dinitrogen hydride and finally ammonia. In order to fix nitrogen, that is to make the nitrogen reacts with the other substances. Several nitrogen fixing bacteria are known and are able to convert dinitrogen N2 to NH3 under mild conditions, that is under ambient temperature and pressure. This is a venture of highly profitable in view of the huge stores of nitrogen available in the atmosphere and that can be put to the use for chemical use both for agriculture and industrial purpose. Metal enzymes have been found to be play a key role in the such processes. Thank you.